Hello everybody, I'm Akriti Kutyala and welcome back to my channel. We are starting a new series on RCC design, reinforced cement concrete, where you will not only learn about the manual design process, but also how to model it in Revit. This series is in collaboration with Novatr, a leading platform that helps civil engineers upgrade their skills with industry-focused courses on BIM, Revit and more. Through this series, you'll gain both theoretical knowledge and practical expertise to excel in the field. So stay tuned, it's going to be an exciting journey.
In today's lecture, we'll be discussing the subject reinforced cement concrete using limit state method. We were discussing the topic design of beams. We'll be referring to the books by Dr. B.C. Punmya and by Dr. Birender Singh. But before that, let's look into the latest jobs in civil engineering domain which have been posted online in about a month ago. So you can see these various postings show us that the requirement is for BIM engineers, BIM specialists, or some sort of BIM specialization which is required by the industry in all these renowned companies. So that is why I recommend looking into platforms like Novatr. They're not just teaching software, they're helping you actually learn how this industry works and with real world BIM workflows. Right now, Novatr is offering exclusive discounts to students of civil engineering with Akriti on their courses, and they've made it super accessible with EMI payment options too. So if money has been a blocker for you, this is your chance. You can finally start building a powerful job-ready portfolio without worrying about paying it all upfront. So grab this opportunity, go to the link given in the description box and access these exclusive discounts. So moving on with our subject, the prerequisites for this RCC subject is IS 456-2000. I hope you have this handy. There are a few membership plans available on this channel where you can access subjects like fluid mechanics and surveying by subscribing to the membership called the Himalayan Birch. And if you subscribe to the membership called the Himalayan Oak, you can access to subjects like fluid mechanics, surveying, steel structure design and drawing. So the link is given in the description box. Go check these out. A quick review of this series. We have completed numerical problems on design of simply supported beams with a simple problem, tension bars cut off, and with side face reinforcement. So in this lecture, we'll be discussing a new topic in which we'll be discussing how to design a cantilever beam with clear span. So let's move on with this numerical problem. So design a cantilever beam with clear span projection from fixed end of 2 meters which carries a superimposed load of 15 kilonewton per meter. Use M20 concrete and Fe 250 steel. So let's look at the problem. The given items are that we have to design a cantilever beam. So it is very important because the design of cantilever beam is different from the design of a simply supported beam. There are slight changes which we have to keep into mind. The clear span here, the question gives you an explanation also that it is the projection from the fixed end. However, we have to understand that this explanation will not be given in the exam. So this is something we need to memorize. Here we've given the value of superimposed load, 15 kilonewton per meter. Unlike the previous questions, it is not mentioned whether it is a live load, superimposed live load or superimposed dead load. But because when we factorize the factorization, the factor is 1.5 for both live load and dead load. So we will not stress over it and we'll just consider it to be simply load. Then another important part which is given is we have to use M20 concrete and Fe 250 steel. This is very important because so far we have been using Fe 415 and we get used to using this value of steel after practicing a lot of questions. But in this particular question, we've been given the value of Fe 250. So we have to be very careful in the exam that what value of steel has been provided to us. So this means that FCK for M20 concrete will be equal to 20 Newton per millimeter square, and for Fe 250 the Fy value, the yield stress, will be equal to 250 Newton per millimeter square. So in this slide you can also see that the environmental exposure conditions are given. We will be assuming this condition because it is not mentioned in the question. So we can assume the condition to be mild, and when we assume the condition to be mild, from table 16 we can see that the nominal cover should be not less than 20 mm. So what we need to do is that the nominal cover should be greater than equal to 20 mm in on all the sides. So this is what these tables are for. Now step 1 is dimensions of the beam. So here we have to keep in mind that when we are talking about a cantilever beam, then generally what we do is we design a cantilever beam as a tapered section. This is how we've been seeing a cantilever beam so far. This is the fixed end and this is the free end. And you have a UDL. This is the bending moment diagram where the maximum bending moment is at the fixed end and the minimum bending moment is at the free end for a UDL. So for cantilever beams, we have to be very specific about the dimensions. So this is tapered and at the fixed end the depth is more. Why is the depth more at the fixed end? Because the bending moment is more at the fixed end. And as we move towards the free end, the depth can be decreased as the bending moment is also decreasing and it is becoming zero in this particular case which is shown on the slide. So here the depth can be less. This is basically done to save the concrete in large buildings. This small amount of concrete which we are saving here helps a lot in the economy of the structure. One more thing which we have to keep in mind is that the beam deflects differently. It does not deflect like a simply supported beam, but it deflects like this. The free end we will have maximum deflection and at the fixed end we will have minimum deflection or zero deflection at times. So this is how the beam is going to deflect. Therefore, the tension phase will be the upper phase and the compression phase will be the lower phase of the beam. This is exactly opposite to what happens in a simply supported beam. So this reinforcement which we'll be providing will be the tension reinforcement, and on the bottom part of the beam here with the reinforcement which we'll be providing will be either anchor bars, or if it is a doubly beam then it will be your compression bars. So that depends on the load. So this we have to keep in mind whenever we are designing a cantilever beam, that we can taper the beam, which is expected of us in the question because we want to understand how tapering is done. And the other part is that the beam will deflect like this with the free end experiencing maximum deflection. The tapering will be done such that the maximum depth is at the fixed end and a lesser depth is at the free end. So designing will be based, or the dimensions which we'll be talking about, the calculations will be done for the fixed end here and not for the free end, because free end has a very less amount of bending moment. So referring to clause 23.2.1, we can see that the basic value of span to effective depth ratio for spans up to 10 meters is different for different types of beams. So this is a cantilever beam and here the ratio is given to us as 7. So what we can do is, while we are assuming the depth, we can assume L by D is equal to 7. So L here is the clear span and D will be the depth. So what we can do is D is equal to or approximately equal to L by 7. L is 2000, that is our clear span, and 7. So this calculates to be equal to 285.7 mm. So D should be greater than 285.7 mm, and remember this D is the effective depth, the small d value which we have chosen. So let us assume that D, we will take a higher value than the required one or than the estimated one here. So let's assume D to be equal to 300 mm, higher than 285.7 mm. Now from the previous slide we know that the nominal cover has to be greater than 20 mm. So we can simply assume that the effective cover is equal to 50 mm. So C effective is equal to 50 mm. So this gives me an overall depth of D plus C effective, which is equal to 300 plus 50, which is 350 mm. So this is 350 mm overall depth. All this is at the fixed end. Whatever values of D we are assuming, they are at the fixed end and not at the free end. So these are the values of D. So next is, we can simply assume that at the free end the value of D can be equal to 150 mm, because we know that we have to reduce the depth here. So we are assuming a value of D is equal to 150 mm because the bending moment at the free end is very less. Now coming to the width of the beam. The width of the beam can be easily assumed or calculated from this value which we have been using in the past simply supported beams also. So D by 2 to 2 by 3 D. So this value computes to be 175 mm to 233 mm. We have to assume a value of width of the beam in between 175 to 233. So we are assuming B to be equal to 200 mm. Now we have the dimensions of the beam with the fixed end equal to 350 mm, the overall depth, the free end equal to 150 mm, and the width of the beam equal to 200 mm. Self-weight of the beam. So when we are calculating the self-weight of the beam, because this is a tapered beam, we cannot just calculate using both the values. So what we do is we simplify our problem and calculate the average depth of the beam. So average depth of the beam is simply the fixed end depth and the free end depth divided by 2. This computes to be equal to 250 mm. Keep in mind that we are using this average depth only to calculate the self-weight of the beam. Otherwise, for all other calculations, we will be using the fixed end depth of the beam. So now the self-weight will be the average depth of the beam, the width of the beam, the length of the beam, and the unit weight of RCC. So from clause 19.2.1, we know that the unit weight of RCC is 25 kilonewton per meter cube, which can be converted into Newton per meter cube as 25,000 Newton per meter cube. Now we have to keep in mind that for this case, the self weight is calculated in Newton and not in UDL or Newton per meter, unlike the previous cases of simply supported beams, because here the length is tapering. So we cannot calculate it just for 1 meter. We have to calculate it for the actual length of the cantilever beam, and therefore this value will be a point load and not a UDL. So here the self weight is a point load. This is very, very important to keep in mind because the calculations will vary in the next steps. We will further be substituting the values of D average and B in meters because this value is in Newton per meter cube. So keeping the units same for the entire calculation. This calculates to be equal to 2500 Newton. So the self weight of the beam, the cantilever beam, is 2500 Newton, and this is a point load. Now the question arises, where will this point load act? So this point load will act at the CG of this entire beam. So now the next step will be to calculate the center of gravity of this beam. So the CG of a cantilever will be equal to the CG of a trapezium or a trapezoid. So the formula is simply the distance between the two ends of the trapezium divided by 3, L by 3 into A. Let's say the longer length is A and the smaller length is B. So A plus 2P upon A plus B. So substituting the values, 0.866 millimeters, meters. This is from the fixed end, or we can simply say this is the X bar value. So we have calculated the CG. Now we know that the self weight of the beam is acting at a point 0.87 meters from the fixed end. Now we have to calculate the factored load. When we are calculating the factored load, we have to be very careful because one is a point load, so we have to calculate PU, which will be 1.5 times 2500, and the next will be due to the superimposed load, that is WU, which will be 1.5 times of 15 kilonewton meter per meter. These values are represented in this figure. So this figure is very important, and knowing that one is a point load and the other one is a UDL is important for the next step, which is calculating the ultimate maximum bending moment. So to calculate the ultimate maximum bending moment, we first need to calculate the bending moment acting on the beam. So for this, we can simply form an equation here, PU into X bar, because this will create a moment here, and this WU, this is a UDL, so that will be WUL, that will be the entire load into L by 2 because it will act at the center. So WU L square by 2. This is the equation which we formed. Substituting the values, we obtain the value of MU, ultimate maximum bending moment, as 48262.5 Newton meter. So we can simply write 48.262 into 10 to the power 6 Newton millimeter. This is the ultimate maximum bending moment acting on the beam. Now we know that we calculate or we design the beam as a balanced section. So in the cantilever beam's case also, we'll be designing it as a balanced section only, and we'll be referring to annexure G and clause 38.1. For a balanced section, we can use this formula. Simply MU will be equal to MU limiting, and MU we've calculated equal to 48.262 into 10 to the power 6 Newton millimeter. So mu limiting is simply taken from an Shear G, where we have to substitute the value of XU max. Now, referring to clause 38.1, we know that for this question we are using an Fy of 250. So the value of XU max by D will be equal to 58. So this value has to be substituted in this equation and a simpler equation will be formed. So substituting, we get mu limiting as 0.148 FCK BD square. We simply substituted this value here and calculated. Now equating these two, we can calculate the value of D required for the given bending moment. So solving for D, we get, so this calculates the D required to be equal to 285.5 millimeters. Now we had, this is for the fixed end, and we had assumed that the value of D at the fixed end is equal to 300 mm. So which is greater than the required value, hence we are safe. Now moving on to the next step, tension reinforcement. If you recall, the tension reinforcement will be provided on the upper end or upper portion of the beam, because the beam is going to deflect like this, and compression will be experienced by the lower end of the beam in a cantilever beam. So we'll be using an Engg G and clause 38.1 to calculate the value of the AST required. So substituting the values in this equation, since we are designing a balanced section, XU by D will be replaced by XU max by D. So calculating AST, we get a value of AST required as 1052.689. So this is the required value of AST. Please keep in mind that the value of D will be the D at the fixed end, that is 300 mm. So this is the required AST. Now we'll be providing it in the terms of bars. So let's try using 20 mm diameter bars. So AST required upon number of the diameter of one bar, or the area of one bar, will be equal to 3.35 bars, but we know that we cannot provide 3.35 bars, so we will have to go to the next integer, which will be equal to 4 bars. So if we use all the bars to be equal to 20 mm, we will have to provide 4 bars. So let's see the distribution. So remember that this is a cantilever beam and the tension reinforcement will be provided on the upper face. We are providing 420 mm diameter bars. So we have to calculate this clear spacing between these bars. That can be calculated using the total width minus the effective cover on either side and the remaining 3 diameters of the bars, which will be divided by the clear spacing, which is 1, 2 and 3. So substituting the values in this formula, we get the clear spacing to be equal to 13.3 mm. So 13.3 mm is not acceptable because we have to provide a minimum spacing equal or greater than the diameter of the bar, the maximum diameter of the bar, which is 20 mm in this case. So the minimum spacing between these bars should be 20 mm, and we do not have this amount of space. So we have to rearrange and re-provide the bars which we are going to use to satisfy this required value of steel. What we can do is we can use this entire AST again and distribute it amongst 2 diameters of bars. So we'll be using two 20 mm diameter bars, and we can use one 25 mm diameter bar. So this is a trial. Again, we will have to check whether it satisfies all the requirements at this stage as well. So this is what we have provided. Let's see that whether these bars, the AST provided by these bars, will be equal to or greater than the AST required or not. So this can be calculated by 2 into pi by 4 into 20 square, area of two 20 mm diameter bars and area of one 25 mm diameter bar. So this calculates to be equal to 1119 mm square. So this is greater than the AST required. So we can go ahead with it and check the bars for spacing. So now we have two 20 mm diameter bars and one 25 mm diameter bar. Let's call the 20 mm diameter bars as phi 1 and 25 mm diameter bar as phi 2. So the equation becomes B minus C effective into 2 minus one 20 mm diameter bar and one 25 mm diameter bar, and divided by the number of spacings 1 and 2, the spacing between these bars. So substituting the value 27.5 mm. this 27.5 mm, we will have to check it against clause 26.3.2. So clause 26.3.2 says that the value of the spacing should be greater than the greatest bar which we are using, the largest bar, which is 25 mm. So 27.5 is greater than 25 mm, and it should be 5 mm more than the nominal maximum size of course aggregate. So nominal maximum size we are using 20 plus 5 gives us 25 mm. Again, this is great, 27.5 is greater than the requirements of 26.3.2 clause. Therefore, okay, so we can provide two 25 mm diameter bars and one 25 mm diameter bar. Now we have to check whether the provided AST is between the minimum and the maximum value of reinforcement given by clause 26.5.1.1. So minimum reinforcement rearranging, we get AS minimum is 0.85 BT upon Fy. Substituting the value, we get AS minimum equal to 204 mm square, which is less than the AST provided, which is 1119. Now calculating for maximum reinforcement, 0.04 B capital T, the overall depth. So substituting the values, 2400 mm square, which is which is greater than the AST provided. So the AST which we have provided falls within the minimum and maximum value. Hence, this is okay. Curtailment of 25 mm diameter bar. In this particular question, it is not explicitly mentioned that we have to curtail any bars, but in the question for cantilever, the examiner generally expects us to curtail the excess bars. Why is curtailment required? If we look at this figure, we can see that the bending moment value keeps on reducing as we move towards the free end. So curtailment simply means to cut off a bar. So let's assume that we are cutting off this bar or curtailing this bar at distance x from the free end. So the corresponding value of bending moment at this point x is mx. We can see that the value of bending moment at fixed end is much higher than the value of bending moment at this point x. So we had calculated the area of steel required as per the bending moment value at the fixed end, because the value of bending moment has reduced here, so the requirement of area of steel has also reduced. Therefore, to save money, we can simply curtail or cut off the bars beyond this point and make it a more economical section. To do so, we have two options. We can curtail one of the 20 mm diameter bars present on either side, or we can curtail the central bar. Now, why will we consider curtailing this central bar and not the extreme ends? Because we have to provide a stirrup also in the near future. When we'll design for shear, we'll be providing a stirrup, and these bars at the end are crucial for it. Fine. So we cannot remove these extreme end bars. So whenever we are curtailing, we'll be curtailing only the central bars. In our particular case, there is only one bar in the center. So according to the requirement for the movement at point X, we will be curtailing the bars. Here we have already decided that we are going to curtail this 25 mm diameter bar because we have placed it in the center. So how will the cross section at XX look like? It will look like this. There will be no bar at the center. Here also at the free end there will be no bar at the center. However, at the fixed end there will be a 25 mm diameter bar at the center as well. So this is the point where we are considering the to curtail the bar. Now, if we see that the free end is 150 mm deep, 150 mm is the overall depth. If we subtract the effective cover, we get an effective depth at the free end equal to 100 mm. Similarly, at the fixed end, we have an overall depth of 350. If we deduct the effective cover of 50 mm, we get an effective depth at the fixed end equal to 300 mm. Now we can also see that FA and EC are equal. FA is equal to 100 mm. So this value EC is also equal to 100 mm. So this gives us the value of CB equal to 300 mm minus 100 mm, which is equal to 200 mm. So we have solved the trapezium. Now, assuming the depth at this curtailment section XX to be equal to the effective depth, that is what we are talking about, is dx. If the effective depth is dx, we have to calculate the value. Now we can write, or we can see that this value of dg, let's say, is equal to AF So this will be equal to 100 mm, and we have to calculate the remaining value of DE. So let's say we call DE is equal to dx dash. We give it another name and call it dx dash. So I can write dx is equal to 100 mm plus dx dash. This is the value of effective depth at distance x from the free end. We have to calculate this value of dx dash to solve for dx. How can we do that? We can simply do that by using similar triangles ACB and ADE. So AC upon BC will be equal to AD upon DE. Substituting the values, we obtain dx dash is equal to x by 10, or which is equal to 0.1 x. Now we can find the value of dx. Dx will be equal to 100 plus 0.1 x. So this is the value of dx. Now we have reduced the entire thing into one variable. Earlier we had two variables, x and dx. Now dx is also in terms of x. So we have simplified our problem. The next point is to calculate the moment available at this point. To calculate this moment, we can again go to annexure G and use the formula given there to calculate the moment at point xx, and we can call it MUX. However, we have to be very careful that the value of AST will be corresponding to the section XX. Both the places here, the AST will be corresponding to XX. That means that the number of bars which are present, we have already decided that we are going to curtail the 25 mm diameter bar. So we know that only 2 bars are remaining here. So AST at XX will be equal to 2 into pi by 4 into 20 square, because the area of steel at XX is corresponding to 220 mm diameter bars, which is equal to 628 mm square. The next part is that we have to keep in mind that the depth or the effective depth will also be corresponding to the X section which we are considering, that is the curtailment section. So substituting the value, we obtain a value of MUX in terms of X, because dx has a value of X here. So solving this further, we obtain 136590 into 60.75 plus 0.1 x Newton meter. Now we have the value of MUX in terms of X. However, there is another way of calculating moment at point X. Again, going back to this formula, the diagram, we can see that this distribution is parabolic in nature. Because this is parabolic in nature, what we can do is we can calculate the value, approximate value of mx at this point from this figure. So how do we do that? Simply by assuming this parabolic distribution. So mx will be approximately equal to mu into x by L. The entire distance is L. So x by L, but square of it. Otherwise, if it would have been linear, we would have just written mx is equal to mu into x by L. But because this is a parabolic distribution, this figure is parabolic. So we are adding a square over here. So x upon L whole square. Please remember that this is an approximate value. So substituting the values, we get 12.065 x square. From the previous part, we know that MUX is also equal to this. The entire equation is in terms of x. We can equate them and obtain this quadratic equation. This quadratic equation can be rearranged into this and be solved for x. So by solving, we obtain a value of x is equal to 1576.79 mm and minus, let's say x1, and x2 is equal to minus 438.54 mm. Because it is a quadratic equation, we will get two values of x. We know that the negative value of x is not acceptable to us, so we will be accepting the value of x1. Therefore, we have the value of point of curtailment from the free end equal to 1576.79 mm. This is from the free end. This can also be called as the theoretical cutoff point from the free end. However, from previous questions, we know that we have to provide a development length LD over here and find the actual cutoff point. To add this LD, we have to calculate the value from the fixed end. This is from the free end. So from the fixed end, the theoretical cutoff point will be 2000, because that is the span, minus 1576.79, which gives us a value of 423.2 mm from the fixed end. This is the theoretical cutoff point from the fixed end. Now we will add the development length to calculate the actual cutoff point from the fixed end. Actual cutoff point will be simply theoretical cutoff point plus LD. How do we calculate this LD? This LD has to be equal to D or 12 pi, whichever is greater. So substituting the values, D will be 300 mm. This is at the fixed end, so the value of D will also be for the fixed end. And 5, we are curtailing 25 mm diameter bar. So the value here is again 300 mm because here the value is calculated to be equal to same. So LD will be equal to 300 mm. This is the value of development length which we have to add to the theoretical cutoff point to obtain the actual cutoff point, 723.2 mm. So this is the point at which we will be curtailing the bar. This is from the fixed end. We can also calculate this value from the free end by simply subtracting it from 2000. This calculates to be equal to 1276 mm from the free end. Now moving on to the next step, we have to calculate the critical section for shear. As per clause 26.2.2, except the clause 22.6.2.1, we have to take the critical section to lie at the face of the support. So the cantilever beam falls in this part of this clause. So the critical section will lie at the face of the support, and unlike simply supported beam, we do not have to add the value of D to determine the critical section. So we'll be calculating the factored shear force. For factored shear force, we know that there are two types of forces. One is a UTL and the other one is a point load. So to calculate the factored shear force at the fixed end, we can simply formulate an equation BU is equal to PU plus WU into L. So substituting the values, I have 48750 Newton. So this is the value of factored shear force. We already know that the factored bending moment at the fixed end is equal to 48.262 into 10 to the power 6 Newton millimeters. So this is the value we have calculated earlier. Now, using clause 40.1.1 for beams of varying depth, the beam for which the depth is varying at every point, we can calculate the value of nominal shear stress tau v from this equation. So substituting the values, before that let's understand that here it is giving us a positive and a negative sign. So further in the clause it defines that the negative sign in the formula applies when the bending moment mu increases numerically in the same direction as the effective depth increases. So if we see at this bending moment diagram, in this direction, the effective depth D is also increasing. The depth keeps on increasing in this direction. So does the bending moment in this direction. So here, because of this part of the clause, we will be using the negative sign and ignoring the positive sign. So this will be a formula. The next part in this formula that we have to consider is this beta. What is this beta? Beta is simply the angle at which the depth of the beam is varying. So to calculate this beta, we can simply solve the triangle PQR. So if I write tan beta for triangle PQR, it will be equal to RQ upon PQ. So substituting the values, I get the value of tan beta is equal to 0.1. So MU we know, VU we know, D and BT are also known to us. These are all at the fixed end. This entire, the value of D and B and again D will be at the fixed end. So substituting the values, tau V is equal to 0.544 Newton per millimeter square. Now from the previous questions, we know that we have to check whether this value of tau v is greater than the maximum shear stress given in table 20 or not. For M20 concrete, the maximum shear stress tau C max is equal to 2.8 and the value of tau v is less than tau C max. Hence this is okay and we can move forward. The next part is to calculate the value of tau C. Tau C can be calculated from table 19. What we have to calculate is the percentage of steel at fixed end. So at fixed end, we can simply write 100 into AST upon BD. So substituting the values, we obtain the percentage to be equal to 1.865%. From table 19, we can see that this value lies between 1.75 and 2. So corresponding values for M20 will be equal to 0.75 and 0.79. We will have to interpolate it for the value of 1.86. So forming the equation, we will solve for Px, which gives us or the value of tau c corresponding to 1.865 will be equal to 0.7684 Newton per mm square. So this value is actually tau c, the shear stress which the concrete can resist. Now if we see that the value of tau v was equal to 0.544 Newton per millimeter square, which is less than tau c. So due to the shear force acting on the beam, the nominal shear stress is lower than the shear stress which the concrete can resist. So there is no need for shear reinforcement. However, we will still provide minimum shear reinforcement to the beam. For that, we can refer to clause 26.5.1.6, where it gives us the value of minimum shear reinforcement. We'll be providing vertical stirrups of 8 mm diameter, 2 leg. So that will give us a value of ASV is equal to 100.53 millimeter square. So this is the value of one cross section of one stirrup. Now using this formula from clause 26.5.1.6, we rearrange it to obtain the value of SV, which calculates to be equal to 273.3 mm. So the maximum spacing which we can provide according to this clause is 273.3 millimeters. However, we have to consider another clause for this maximum spacing, that is clause 26.5.1.5, which says that the maximum value of spacing can be 0.7D, 0.75D or 300 mm. So calculating 225 mm and 300 mm. So now we have three values of maximum spacing for the stirrups given by these two clauses. We have to take the least value. The least of these is 225 mm. However, providing a spacing of 225 mm in the field is difficult. Therefore, we adopt a spacing lesser than this maximum spacing. So let us assume this to be to the nearest lower value of a multiple of 10, that is 220 mm. So SV max or the spacing which we are going to provide is 220 mm. Therefore, provide 8 mm diameter 2 leg vertical stirrups at 220 mm center to center. Now we have to calculate the shear force at the cutoff point. So to do that, first we have to determine the value of y1 and y2. So to calculate y1 and y2 is very simple. Y1 is equal to 150 mm and y2 we can calculate from similar triangles ADE and ABC. So solving, y2 will be equal to y2 is equal to 128 and y1 is equal to 150 mm. So depth at distance 1276. So curtailment point is 278 mm. So the depth of the beam at 1276 millimeter from free end is 278 millimeters. Now what we have to do is we have to calculate the shear force diagram. Why am I saying shear force diagram? Because here we have a UDL and a point load, if you remember, in this cantilever. So the point load is acting at the CG of the beam, which is 1.133 meters from the free end, and the UDL is acting throughout the beam. So we need to find the shear force at the point 1.276 meters from the free end. That is the cutoff point. So at this cutoff point, to obtain the shear force, we need to use the traditional method and we cannot use the similar triangle method, because here you can see that there is a vertical change in the shear force. So let's form the equation. Considering the value of shear force at this cutoff point to be equal to Vu1, we can see that this point, if we extend it to the beam to understand, this will be the point where we are considering our shear force. So there will be shear force due to Pu and shear force due to Wu. So substituting the values in this equation, we get Vu1 is equal to 32460 Newton. So this is the value of shear force at the cutoff point. Now we'll calculate the percentage of steel at the cutoff point, which will be P is equal to 100 into AS1 upon BT. So this AS is corresponding to the cutoff point. If you remember in the previous calculations, we had calculated this value to be equal to 628 millimeters square corresponding to 220 diameter bars. Now while substituting the values, we have to keep in mind that the D here, because we are calculating the percentage of steel at the cutoff point, so the depth which we will be using should be corresponding to the cutoff point which we have calculated above in the previous slide. So this value is equal to 278 mm. Here this is important to note, this calculates to be equal to 1.38%. So now we have the value of percentage of steel. So from table 19, we can calculate the value of tau C. So to calculate the value of tau C, let's see at table 19, the value falls between 1.25 and 1.50 for P, and we have M20 concrete. So these are the values of tau C. So interpolating these values corresponding to 1.38. We form the equation, and this calculates to be equal to tau C1 will be 0.696 Newton per mm square. So this is the value of the shear resistance given by concrete at the cutoff point. So this shear resistance at the cutoff point will be because of two elements. One is the concrete which is present. We have calculated this value, and the shear resistance due to the stirrups. If you remember, we had provided stirrups at nominal size and spacing of 220 millimeters center to center. So now we can substitute the values for shear resistance due to concrete. The resistance will be equal to tau C1 into B into D1, or the value at cutoff point. And for the stirrups, it will be 0.87 F by ASV into D upon SV. So this is the value of stirrups which we have already provided. So we'll be considering that value. Again, remember that the D here will be the D provided at the cutoff point. So this is important while substituting the values. So on substituting the values, we have obtained the total shear resistance equal to 55120. I'm sorry, the correct value is 54397.6 Newton. So this is the value of shear resistance which we have. Now, as per clause 26.2.3.2, so the shear at the cutoff point does not exceed 2/3 that permitted, including the shear strength of the web reinforcement provided. So we have included the shear strength of the web reinforcement provided, so it should not exceed the 2/3 of the permitted value. So first of all, let's calculate the value of 2/3 of shear resistance, which is equal to 2/3 of 54397.6. This calculates to be equal to 36265.06 Newton. This value should not be less than the value which we have calculated for the shear force at that point. Which is the shear force at that point? The shear force at that point is 32460 Newton. So this value which we have provided as resistance is greater than the shear force acting at the cutoff point. Hence this is okay. If in case this value was lesser than the shear resistance, we would have to provide additional stirrups, because here there is no such problem and the value is greater, so no additional stirrups are provided or required at the cutoff point. Now we look at the development length of the bars. For that, we'll consult clause 26.2.1. So the development length is given by LD is equal to phi sigma S 4 tau BD. But because this is limit state, we can replace sigma S by 0.87 Fy. So the formula will become 0.87 F by phi upon tau BD. So for tau BD, we have to refer to table 26.2.1.1. So as per table 26.2.141 or clause 26.2.141 for M20 concrete, tau BD is equal to 1.2. And then the clause further says that for deformed bars conforming to IS 1786, these values shall be increased by 60%, and in case of compression, it should be further increased by 25%. However, if you remember, we are using Fe250 steel. So that is mild steel. For mild steel, we do not have to increase this value, but for HYSD steel, we'll be increasing this value by 60%. So for our case, at the moment, tau BD is equal to 1.2. 2 Newton per millimeter square. Phi is equal to the diameter of the bar, which is 20 mm, and Fy is already 250 mm. So substituting these values, we obtain a development length requirement of 906.25 millimeters. So now, in order to develop full tensile strength at the face of the support of each 20 mm diameter bars, this must be embedded. This length must be embedded into the support by a length equal to 906.25 mm. So how do we provide that? If you look at this figure, this is the face of the support, the dotted line, and we have to provide a length of 907 approximately mm beyond this face of the support. We know, or we can assume, that the width of the support is equal to 400 mm. So we have to calculate this value. What we can do is we can extend it, then provide bends of 90 degrees. Because the value of 907 is too large, therefore we have to provide two bends. Otherwise, we could have done it with just a single 90-degree bend and left it here. For that, since this question does not mention the width of the support, we are assuming a value equal to 400 mm. Now, whenever we provide a bend, there is a standard length which gets in, which we have to calculate. That is, which this bend requires, length of the bar, which can be seen in red here in the figure. For each 90-degree bend, we say, or we calculate the anchorage value to be equal to 8,5. Anchorage value is from the point where we have started to bend the bar until we have stopped bending this bar. So this 8,5 value, phi is the diameter of the bar we are bending, is provided as the anchorage value, or calculated as the anchorage value for every standard 90-degree bend. So here, since we've decided to provide two bends of 90 degree, you can see that in this figure we have this 8 mm 8,5 anchorage value here and 8,5 anchorage value here. In this also, we have to keep in mind that when we are calculating the anchorage value, there is this horizontal distance which the bar has traveled. If you can see, I started bending the bar from here, this point, and I ended bending it here, but there is some horizontal distance which the bar has traveled. The curved distance is 8,5, but the horizontal distance is equal to n plus 1 phi. So n plus 1 phi. Now the value of n is equal to 2 for mild steel bars and is equal to 4 for HYSD bars. Since in this particular question we are using Fe250 steel, so the value of n will be equal to 2. So this horizontal distance which we are talking about here, from this point where we have started bending the bar up to the point where this bar has been bent, this is equal to n plus 2 phi, which will be equal to 2 plus 1 phi, which is equal to 3 phi simply. So if we calculate, if I am saying that this is distance x, so I can write this is equal to 3 phi. Already phi is written, so we can say it to be 3 phi. So this distance x can be calculated. Now what we can do is we have to find what is this length. This length from the face of the support up to the point we are bending the bar. To calculate that distance, what we can do is, this is the total length of the support. So the total length we have is 400 mm. From that, we have to subtract the clear cover here. So assuming the clear cover to be equal to 20 mm, so I can write that 400 minus 20. Now beyond this clear cover, there is another horizontal distance which we are traveling, which is 3 phi. So that has to be subtracted as well. So I will be subtracting a distance of 3 phi. This is the total horizontal distance which I will be traveling from the face of the support up to this point. And because I have subtracted 3 phi, I have come to this point. So when I calculate this value, we obtain it equal to 320 mm. So this distance which the bar has traveled from the face of the support up till this point from where we have started bending the bar is 320 mm. Now total length which is available to us can be calculated by adding this 320 mm, this 8 phi, and also we have to know what is this distance, the distance which we have extended. So how can we calculate that? To know that value, we know the depth of the beam at the fixed end, which is equal to 350 mm. From this 350 mm, we know that 50 mm is the cover over here, and 50 mm is the minimum cover which we have to provide here. Then some distance will be left out for the bending as well. So 8 5 here, 3 5 here, 3 5 here. So approximately I am assuming that this distance can be taken equal to 100 mm. For my sake, I am assuming this value. If the length is more, then you have to calculate this value further. So now I am again traveling a distance of 8 5 and this extra value is left. I don't know what value this is. So let's calculate this value. What do we have to provide? We have to provide a length of 907 mm from the face of the support. If we look at from the face of the support, we travel a horizontal distance of 320 mm. So from this equation, we can calculate x, which computes to be equal to 167 mm. However, we can just increase it slightly to 175 mm, and thus the total value which we have provided LD will be equal to 915 mm from the face of the support. Since we have provided this value greater than the required 907 mm, hence we are safe and this is okay. If by chance the value was not sufficient, the length of the development length which is required could not have been provided, then we could have extended this x to a greater value and increased the value of 100 as well as per the permissible range here after excluding the covers. The last step is to check for deflection. So to check for deflection, we again need to calculate the percentage of steel. At the face of the support, the area of steel is 1119 mm square. So substituting the value, the percentage of steel is 1.87%. Now from figure 4, we can calculate Fs, which is 0.58 F by AST provided upon AST required. AST required upon AST provided. This calculates to be equal to 136.45 Newton per mm square. So we have the value of percentage of steel and Fs. From figure 4, we have to determine the value of modification factor. So if we look at this figure 4, for 1.87, we can approximately write it to be here, and then if we move to 1.36, the modification factor is approximately equal to 1.2. Now from previous numericals, we know that for deflection, we need to see from clause 23.2.1 what kind of beam we are designing. So here we are designing the cantilever beam and the span is 2 meters, so less than 10 meters. So this value will be equal to 7 into kT into kc into kf. Kt is the modification factor for tension, Kc is the modification factor for compression. So because we are not providing any compression bars, so Kc will be equal to 1 and the beam is not flanged. So again, at every cross section the beam is rectangular. So the factor Kf will also be equal to 1. So substituting the values, the ratio of L by D max calculates to be equal to 8.4. This is the maximum value which is permitted by the code. And what we have provided is L by D provided is simply 2000, which is the clear span, divided by the depth at the fixed end, which is equal to 6.67. We have to keep in mind that while checking for cantilever, we will be checking at the fixed end. So this value is less than the maximum value, hence it is okay against deflection. So this brings us to the end of the question, where we can see the detailing of the question. We have at the fixed end the depth is 350 mm and 200 mm is the width. At the free end the depth is 150 mm and the width is 200 mm. There are 3 bars, 2 20 mm diameter bars and 1 25 mm diameter bar. At the top here, this is the tension face of the cantilever beam. At the free end, because we have curtailed the 25 mm bar, we cannot see it. There are only 2 20 mm diameter bars. 2 anchor bars of 12 mm are provided at the base on the compression face. In the L section, we can see that the beam is tapering, and at a distance of 1.276 mm, we have cut off this bar. This particular symbol, which it is shown, means that the bar has been cut off. We can also see the LD that has been provided. The detailing of the LD we have discussed in detail here. You have to provide this detailing as well at the end of the question. We are providing 8 mm two-leg stirrups at distance 220 mm center to center. Width of the support has been assumed to be 400 mm. The distance of curtailment from the face of the support is 7.23 mm. So this is the detailing which we have to provide at the end of the question. So in this question, we covered cantilever beam with the tension bars cut off. I hope you like the lecture. Thank you. Like, share, subscribe, and join the membership program.
All right, so this time we do have cantilever beam, clear span is 2 meter, superimposed load, and grades of concrete, and still we do have. So let's model this in Revit. It will be little interesting that we will be adding reinforcement in trapezoidal beam, not the rectangular one. So let's just see it. How can we do it? Okay, as you can see that I have already modeled column and beam. Okay, this is the elevation. This is how it will look like in plan view. Okay, I have cut the section to the proper area, so we can just add the reinforcement in better view. So this is what our better view to add the reinforcement. So very first thing we'll do is to add the cover. I'll go to structure, under reinforcement there is an option cover. Okay, I'll select the element for the cover. Here cover settings, we'll go with the 20 mm, and then we'll go to rebar. As always, we'll go first with the stirrup part. We'll have the shape. This one is the good one. 10 mm let it be. And first set the placement after adding the size. And you can hover the mouse to set the angle. You need to adjust it a bit. Okay, as we'll be doing in trapezoid, it will be little complicated. Okay, now if I see this in elevation view, we can see that, okay, to make it in trapezoidal shape, so we'll go to set type, varying rebar set to let it adapt the shape. Then we'll go to number and spacing, as we know that how many stirrups are there. So let's make it 12 with 220, right? Center to center. We need to adjust it a bit. Okay. Cool. So after doing it, our stirrup part is done. This is how you will see in 3D view. Next step is to add this 20 mm bars at the corners, right? To do it, structure, rebar, will go with typical shape. Size will be 20. And the placement will be parallel to the cover. And let it be first single. Then we will just edit it later on, and then we'll mirror it or copy it. Okay. This is, we can double click it and edit the rebar. Okay, let me make it up to this. Okay.
Where's that?
We will make sure that this will look like this. Okay, so this will be 100, this will be 175. Okay. So first, let's keep it. I just check the, okay, let's make it 230 to make it, okay, 235. That will make this 175, and this should be 100. So let's reduce this 50. Let's make it 20. Right, this is appropriate, I guess. You can again go to this and check that if it's all proper or not. It seems proper. Now I'll just go to this view and I'll just mirror this under modify. From this I'll draw the axis and then go to elevation and just edit it, because we want here slanted. So I'll just drag and put it like this, and let's make it up to this, and we'll add. Okay, yeah, it seems not correct, right? So to see this, I'll go to the cross section view and just adjust it manually, right, to make it appropriate. I'll again go to elevation.
To dawn.
Okay, now I can make it. Okay, it's not coming properly. I can redraw it. Sometime it will happen.
How to put
Okay. So it's done. Now I'll just select this too. We also want at this corner, left hand side. So I'll just put it with this axis. And now only thing remained is this 25 mm bar, which will be at center. So I'll just copy this. Okay. And if it's not aligned, I'll just align it with, this axis, and this bar is created. So this is how you can just, rebar adjustments, modeling as per whatever the requirements are there. Okay. It is little difficult than the conventional rebarring, the rectangular rebarring, but it's also so interesting to know that how can we just, customize it in Revit. So thank you so much for watching.